So in today's lessons, we're going to be talking about specific heat. And to get us started, I want you to think of two things. I want you to think of a glass of water. And here's a glass of water, and it sounds very refreshing right now. And I also want you to think about a lake. And so here is a huge, giant lake, and it's filled with water, which also sounds very refreshing right now. Okay, and then there you are swimming. Okay, so a glass of water and a huge giant lake. Which one of these would be harder to heat up 1 degree Celsius? Which one would be harder to make all of the water in the entire sample heat up 1 degree Celsius? And I'm hoping that you realize that it would be much harder to make this entire lake, which is huge, heat up by 1 degree Celsius than it would this tiny glass of water. Because it wouldn't take as much heat. There's not as much substance in the glass of water as there is in the entire lake. And so when you think about these two things, we know that there must be something different about them when it comes to heat. That one of them can absorb heat very easily, like the water, and one of like the glass of water, and one of them it takes a huge amount of energy to raise its heat. And this idea that different amounts of a substance require different amounts of heat to heat up is called heat capacity. The amount of heat that is required to raise the temperature of the substance by 1 degree Celsius. So to raise this glass of water 1 degree Celsius is the glass of water's heat capacity, and the energy needed to raise the temperature of the entire lake by 1 degree is the lake's heat capacity. And so obviously the lake has a much greater capacity to absorb heat than the glass of water does. And heat capacity depends on two different things, and I hope by this demonstration you realize that mass, or the amount of substance, is one of the big factors that affects the heat capacity. But the second one is the type of substance. I think all of you have boiled a pan of water and realize that that pan of water takes a lot of time to heat up. So type of substance. However, if you just put a pan on the stove and turn the stove on, that pan heats up very, very quickly. So the metal pan takes very little amount of heat to make it heat up, whereas a pan of water takes a long time to heat up. The water absorbs a huge amount of energy. So the mass of the substance affects the heat capacity of the substance, and the type of substance affects the heat capacity of the substance. Sometimes we want to take mass out of this equation, though. Sometimes we don't care about the mass because, for instance, a glass of water and a lake of water both contain water. And so sometimes we just want to compare water to water, and both of them have the same amount of capacity for absorbing heat if you compared the same amount of lake water to the same amount of a glass of water. And so sometimes we want to get rid of this idea of mass, and when we get rid of this idea of mass, then we're going to talk about specific heat capacity. Specific heat capacity gets rid of that mass idea. So specific heat capacity. And often specific heat capacity is just referred to as specific heat. And this is the amount of heat that is necessary to raise 1 gram of a substance 1 degree Celsius. And it's given the symbol C, capital C, for specific heat capacity. And so specific heat capacity equals the amount of heat that it takes to raise 1 gram of a substance, so mass, by 1 degree Celsius, which is change in temperature. Remember that delta sign? That delta sign, that triangle, means change. So it's the amount of heat to raise 1 gram, which is your mass, by 1 degree Celsius. So if we look at our units here, heat we've been talking about in joules or calories. Mass we've been talking about in grams. And change in temperature is degrees Celsius. Or you also could use Kelvin, because when you find the change in temperature, Kelvin and degree Celsius are identical. So we have two different units that we can use. We have joules per gram degree Celsius or calories per gram degree Celsius. And you'll notice if you just look at the units for specific heat, we have the equation joules, Q, heat, grams, mass, and degrees Celsius, temperature or change in temperature. Okay, so let's look at this a little bit closer and see if we can identify some different parts of this equation. So if we want to find the specific heat of a substance, we need three different measurements: heat, mass, and temperature. So our change in temperature. So Q is simply the amount of heat that a substance absorbs. Mass is going to be measured in grams, and that's a very easy measurement. Just put the substance on a balance. Delta T has two measurements involved. Delta means change, and that always means your final minus your initial. So we need to take the final temperature, the temperature after we've heated it up, and subtract the initial temperature, which is the temperature before we heated it up. And that will allow us to calculate delta T, the change in temperature. So if we measure the heat, divide by the mass in grams, and divide by the change in temperature, we know the specific heat of the substance. So let's try a problem here and see if we can solve for the specific heat of a substance. Here's our substance. It takes 523 joules of energy to heat 15 grams of a substance from 25 degrees Celsius to 50 degrees Celsius. What is the specific heat? So the first thing we want to do is write down our givens. We're given the heat, which is 523 joules. We're given the mass, which is 15.0 grams. We're given the initial temperature, which is 25 degrees Celsius. And we're given the final temperature, which is 50 degrees Celsius. The unknown, what we're solving for, is the specific heat, which is C. That's what we don't know. So the next thing we want to do is write down our equation. Our equation is specific heat equals Q over M delta T, M times delta T. And now we're going to substitute in. We're going to substitute what we know. So specific heat equals the Q, 523 joules, divided by the mass, 15.0 grams, divided by the change in temperature. And our change in temperature is final minus initial, 50 minus 25, which is 25 degrees Celsius. And so now we do our division, we do our math. 523 divided by 15 divided by 25. And when you do that, you'll get the specific heat of the substance, which is 1.39 joules per gram degree Celsius. And notice my units are just the units that were in the equation, joules per gram degree Celsius. And so that's my final answer. Significant digits we need to check: 3, 3, and only 2, so we should have only 2 significant digits. So 1.4 joules per gram degree Celsius. And so that's the specific heat of our substance. So let's do one more practice problem, and in this one we're going to look at water, and water is going to be used over and over and over again. So this is a really important value of specific heat right here. Water's specific heat is 4.184 joules per gram degree Celsius, and you're going to see this over and over and over again. So I would recommend you writing it in your notes because you're going to see it over and over and over again. So in this problem, the question is asking how much heat will be released when 45 grams of water cools. And this time we're cooling something rather than heating it up, from 45 degrees Celsius to 15 degrees Celsius. So again, we're going to use the guess method. We're going to write down what's given. So first, we're given mass, and the mass is 45 grams. The second thing we're given is the initial temperature, right here, from 45 degrees Celsius. So that means it's its initial temperature, which is written right there. Our second is 15 degrees Celsius, which is our final temperature. And then another thing that's given to us in this equation is the actual specific heat of water. So I'm going to go ahead and write that down. The specific heat of water is 4.184 joules per gram degree Celsius. So that's what's given to us, and what we're solving for, our unknown, is heat, which is Q. And so if you remember our equation that has all of these variables in it, it's our specific heat equation. C equals Q over M delta T. Now I'm going to rearrange this in terms of just Q by multiplying both sides by M delta T. I'm going to multiply this side by M delta T, and I'm going to multiply the other side by M delta T. And what I'll end up with when I do this is I'll end up with a very common equation that you'll see many times, which is Q, because Q is left by itself now, equals MC delta T. MC C delta T, which kind of looks like Q equals MCAT, except the A is actually a delta sign. This form of the equation is one that gets used over and over and over again because we're often solving for Q, the heat of a reaction, or the heat of a process. And so let's go ahead and solve this problem. We're going to solve for Q. So Q equals, we're going to substitute 45 grams times the specific heat of water, which is 4.184 joules per gram degree Celsius, times the change in temperature. Now be careful with your change in temperature. Remember, change in temperature, delta T, is always final minus initial. So 15 minus 45. So when we do 15 minus 45, you actually get negative 30 degrees Celsius. Not positive, it's always final minus initial, so negative 30 degrees Celsius. And so when we solve this problem, we're going to multiply 45 times 4.184 times negative 30. And notice our grams will cancel, numerator and denominator. Our degree Celsius will cancel, numerator and denominator. And that leaves us with joules. So when you do this, you will get your final answer, which is 5,648.4. So 5,648.4, and our unit is the unit left over, which is joules. Now, significant digit-wise, we want to round for significant digits, and our least significant digits in our problem are 2. So we should only have 2 significant digits in our final answer, which gives us 5,600 joules. And so that's how much heat will be released when 45 grams of water cools down by 30 degrees. 5,600 joules. Easy, right? Okay, well, that's where we're going to stop for today with specific heat, and good luck to you in the future.